Hello, sir. I'm Eren. We will make presentation. Next page. Overview of contents, introduction, background, literature review, potential vulnerabilities, recommendation for improvement, conclusion. To purpose, to monitor and record environmental conditions in real time, to provide accurate and continuous data for decision-making process, to support environmental monitoring by supplying reliable sensor-based information, to aid agricultural management through precise data collection and analysis, to contribute to disaster detection by enabling early warning systems, to assist in the development of smart cities by enabling integrated responsive infrastructure. Which areas are WSNs used within? Environmental monitoring, agricultural management, disaster detection, and smart cities. Rising importance due to sustainability goals, climate change mitigation, efficient resource management, and benefits of optimized WSNs. One, flexible, two, scalable, three, energy efficiency networks, and four, help governments, industries, and researchers make informed decisions.
VSNs are critical technologies used for monitoring environmental conditions such as temperature, humidity, and air quality. These systems consist of wirelessly connected sensors nodes that collect and transmit data to a central hub for analysis. VSNs are especially useful in locations where traditional monitoring systems are costly or impractical to install. Originally developed for military purposes like surveillance and battlefield monitoring, VSNs have become widely used in civilian and industrial applications such as agriculture, environmental research, urban in- infrastructure, and disaster management. Each sensor node typically contains a sensor microcontroller, wireless communication module, and power source, often powered by batteries or energy harvesting methods like solar panels. Because these devices have limited energy, techniques like duty cycling are used to conserve power and extend network lifespan. One of the key challenges is communication reliability, as wireless signals can be disrupted by obstacles on or interference. To overcome this, robust network topologies like mesh networks are implemented, allowing data to reroute if a nodal fails. Recent advancements have integrated VSNs with the Internet of Things and edge computing, enabling local data processing that reduces both energy consumption and latency. Additionally, machine learning is increasingly being used to analyze patterns and make predictions, enhancing systems intelligence. Security remains
Literature. Huh?
Security remains a concern, especially in exposed environments, and is addressed using lightweight encryption and secure protocols. As VSNs evolve, they are becoming more autonomous and integral to smart systems in various domains. Yes.
Literature review. Wireless sensor networks are systems made of small sensor nodes that monitor and transmit environmental data with improvements in wireless communication and sensor tech. VSNs have become widely used in areas such as agriculture, military, health monitoring, and smart cities. Next, VSN architecture. VSNs are designed to operate with limited energy and processing capabilities. Traditional networking protocols aren't efficient for such constraints. Instead, custom lightweight communication stacks are used to improve performance and minimize energy consumption. Next, energy efficient routing. In VSNs, routing protocols are tailored to save power. Cluster-based methods help distribute energy usage fairly among nodes. This not only extends network life but also ensures more stable communication over time. Next, data management and security. To save energy, sensor data is often aggregated before transmission. However, this may reduce accuracy. Security is also challenged due to open and often unprotected deployment of sensors, making lightweight encryption and trust management essential. Next, scalability and diversity. As sensors networks grow, managing communication and consistency becomes more complex. Some VSNs use different types of nodes with varying power and processing levels to enhance overall performance. Through this adds to system complexity. Next, IoT integration and power. With the rise of the Internet of Things, VSNs are now expected to interact with broader in systems. To overcome battery limits, renewable sources like solar and kinetic energy are used for powering sensors supporting longer operations. Next, localization and reliability. Knowing the location of each node is crucial for many VSM applications. Since GPS is often impractical, alternative techniques like signal strength or timing are used. Networks are also designed to handle node failures using self-recovery mechanisms. Next, future outlook. Future VSNs will leverage artificial intelligence for autonomous decision making and optimization. Enhanced energy harvesting, smarter protocols, and seamless integration with IoT ecosystems will make VSNs more intelligent and sustainable.
Hello everyone, I'm Salih. I will be representing the key security vulnerabilities in wireless sensor network, also known as WSNS. To begin with, VSN technology is becoming increasingly widespread in various areas such as smart homes, hospitals, military zones, commercial industries, and agriculture. These systems are made up of small sensors that collect and transmit data wirelessly. Although this might seem simple, the technology comes with serious security challenges. I will walk you through the 5 most critical security risks that I have identified in my research. First one, exposed physical access. Next, the first issue is physical exposure. Sensors are usually placed in open public environments, making them easy targets for tampering, unlike personal devices. These sensors are not locked or protected. For example, in conflict zones, someone can open a sensor and extract encryption keys or physically destroy it. Solution to this, sensor should be encased in tamper-resistant materials like epoxy and should include mechanism to destroy sensitive data automatically if tampering is detected. The second one is eavesdropping. Next, because WSNs rely on wireless communication, they are highly vulnerable to interception. If the data is not encrypted, anyone with the right tools can capture and read it. For instance, in a hospital settings, patient data could be intercepted, violating privacy. Solution to this, use strong encryption method like AES 256 and update encryption keys regularly. Protocols such as TLS also can support and protect transmitted data. And third one, Sybil attack. A Sybil attack happens when a single sensor node creates multiple fake identities in network. This manipulates the system trust and can disrupt data filtering and energy disruption. For example, think of it like a one person joining a group chat using 5 different accounts to mislead others. Solution implements strict identity verification through signal certificates or location-based authentication methods like RSSI, receive signal strength indicator. The fourth one, denial of service attack. Those attacks aim to overload the network by flooding it with traffic. Since WSNs have limited battery and processing capabilities, this kind of attack can quickly drain energy or cause crashes. For example, a malicious node sends constant fake requests overloading the system. Solution, set message rate limits and implement anomaly detection using AI or behavioral monitoring. And the last one is routing attacks. Routing attacks manipulate the data path sensors. This affects how and where information flow in the network. Types include sinkhole attacks, wormhole attacks, selective forwarding. Solution to these attacks, use multiple routing paths, simple stamp, base hop checks, and real-time monitoring to identify unusual behavior. To conclude, while VSNs are powerful and practical, they also pose several serious security challenges. Physical tampering, data encryption, identifying spoofing, DOS attacks, and routing manipulation are among the top threats. Thank you.
Are recommended. Energy efficiency, develop low-power hardware with adaptive sleep or wake algorithms and energy harvesting capabilities. Security, use for lightweighting cryptographic for light ACC ensure secure key management, routing or topology, design routing protocols resistance to common attacks and support quality of security. Energy harvesting integrates solar vibration or RF energy sources. Physical protection use tamper-resistant design and distributed authentication. Software updates establish secure, energy-efficient update mechanism. And backup or recovery ensure regular backups and strong recovery plan. Next page. Recommendation for improvement: energy efficiency, security, routing resistance, energy harvesting, physical security, software and firmware maintenance, and backup or recovery planning. Next page. These are examples of energy-oriented hardware and adaptive data cycle. Next page. These are examples of elliptic curve cryptography, ICC encryption, same security, RSA encryption. Next, please. These are symmetric encryption examples, secret case, same case. Next, please. Conclusion: wireless sensor networks are critical for data collection from inaccessible or hazardous areas. Energy efficiency, routing, and security are key factors in wireless sensor network designs. Energy harvesting and wireless power transfer will extend wireless sensor networks' lifetimes. Standardization and interoperability are essential for scalability. And finally, integration with IoT and advance in AI will drive in the future of wireless sensor networks. Next, please. Thank you for listening.